Our first speaker this afternoon is a team from the National Weather Service of Sean Weigel and Jeremiah Pyle. Mr. Weigel is a meteorologist and lead forecaster with the National Weather Service in Portland. Sean's been with the National Weather Service for almost 10 years. Maybe Sean's not here. Okay, well, we'll keep going then. He's a Penn State graduate, spent several years forecasting on the East Coast before returning home to the West Coast in 2003. After a 3-year stint as a forecaster and incident meteorologist with the Monterey, California National Weather Service office, Sean moved to Portland in 2006 and has appreciated the forecast challenges of the Pacific Northwest ever since. Mr. Pyle is also a meteorologist with the National Weather Service in Portland. He's been in Portland for just over a year and was previously stationed at the National Weather Service in Massachusetts. Jeremiah received a bachelor's degree from Dartmouth College and a master's degree from the University of Massachusetts. Having grown up in the Midwest as a severe weather junkie, right on, he is quickly realizing that predicting thunderstorms is nothing compared to forecasting the bizarre behavior of Pacific Northwest marine stratus. Ladies and gentlemen, please welcome Sean Weigel, maybe, and Jeremiah Pyle.
Okay, I'm Jeremiah, and first of all, I'm going to address the obvious absence of Sean here this afternoon. Yesterday afternoon, he realized that his alma mater, Penn State, is playing football on ESPN2 today. This morning, he called in sick with the stomach flu, so is there a connection? I don't know. So it's just going to be me today, soloing it. So I'm going to talk to you a little bit about a couple of exciting new developments we have here as meteorologists in the Pacific Northwest. A new coastal radar that we've got, and a Dual-Pol technology upgrade on our radar. So, first I'll talk a little bit about our new radar. It's located at Langley Hill, Washington, and it was just dedicated this past month on September 29th. It's pretty close to Grays Harbor, Washington, so right there on the South Washington coast. This has been a long time coming. It's a joint effort between our agency, NOAA, the University of Washington, and Congress, notably Senator Cantwell from Washington. This new radar is equipped with our legacy Doppler technology, the technology we've been using for years, and it's also got the new Dual-Pol upgrade as well, so very powerful new tool. So how does it benefit us here? Well, before this, our radar was located near Scappoose, Oregon, on Dixie Mountain, and it's actually elevated a couple thousand feet, so we kind of had a bit of a blind spot along the coast. We weren't able to see down at low elevations on the coast, so oftentimes precipitation, low-top precipitation was able to sneak up on us without us being able to see it on radar. So this our new radar should help with that quite a bit. We can now detect precipitation well offshore, much further than we could before, sometimes as far as 100 miles offshore before it gets into us, so we're able to predict it a little better now. Also, another interesting feature with this radar is we've got an experimental 0.2 degree elevation scheme, where most radars, their lowest gain is 0.5 degrees above the horizon. This is significantly lower, so we can see even lower down, close to the ocean surface. So just for a little comparison here, with our new radar, we can see very close down to the Earth, to the surface of the ocean. Depending on where you're located, how close you are to the radar, you can see down as low as 1,000, 2,000 feet above the ocean. Whereas with our previous radar, we were limited along the North Oregon coast, we could see approximately 6,000 feet above mean sea level. And on the southern Washington coast, it was even worse. Our lowest elevation scan was about 10,000 feet. So it's a significant improvement for us in these locations. Okay, so I'm going to show you a couple of recent radar images from this radar. We've had it only about a month, but we've already had a couple of interesting cases where it's benefited us. So this here is a velocity image. Hopefully a lot of you are familiar with what velocity is from radar. It's basically telling us what the wind speeds are like. And what we can see from this animation, if I can shine my laser here, we've got basically our radar is located right here. So down south of the radar, we've got greens and blues. That's indicating you can see our velocity scale over here, that's indicating motion towards the radar. So that's southerly wind there. And again, if you go north of the radar, you've got more of these reds. So that's indicating away from the radar. So we're looking at strong southerly flow. And based on this area here, we have some really deep shades of blue. Looking over at our velocity scale, that's indicating wind speeds in the 60 to 70 knot range here. This is very close down to the surface of the coast. So based on this image here, we were actually able to make some updates to a high wind warning we had out for this region that we never could have been able to do in the past with our old radar. So already we've had, this case here, we were able to utilize our new radar. And actually this is fresh off the press. Yesterday, if you'll remember, we had some rain and it was caused by a front pushing on shore. This is radar data from that front yesterday. We threw it in here at the last minute. And basically, the features of interest that we're looking at here is there's this area here of bright green. So that's telling us that we have fairly strong winds in this region here. So looking at that, we were able to get a really good estimate of what kind of winds we were dealing with and what we could expect to be moving on shore shortly afterwards. Also of interest, you can see there's a pretty well-defined line here. That's showing us where the actual frontal boundary is itself. So that's pretty powerful. We never could have seen that with our old radar. So this new coastal radar is already making, it's having big impacts on our forecasts. Here we just drew in the front. So we were able to identify the exact position of that front based on the radar data alone. Okay, so I'm going to transition from there to talk a little bit about our dual polarization upgrade. And I apologize, this is fairly technical in nature inherently. I tried to make it as non-technical as possible, but there's still going to be some parts that may be a little confusing. So if you find yourself zoning out, maybe just blink out for a couple of seconds and then come back to me. I'll try to get back on point so everyone can understand what I'm talking about. So the first thing I want to say is just talk a little bit about how radar works for those of you who don't know, and then discuss physically what's different about our dual polarization radar versus our traditional Doppler radar. So over here on the left, you've got an image of a radar dome. That's what our radar looks like. Basically a giant soccer ball on a tower. And how it works is that soccer ball, it emits electromagnetic pulses, shoots energy out into the atmosphere, and anything that's out there in the atmosphere will reflect part of that energy back to the radar. So when the radar receives energy back, that tells us that there's something out there. So that could be anything from cloud particles, precipitation, to things like birds and insects. So there's a large variety of objects that our radar can pick up on. So our traditional radar had what's called horizontal polarization. And it's not important that you really understand what that means. But basically, the electromagnetic pulses are oriented in the horizontal direction. So with the animation again. So this is our conventional Doppler radar. It's got one type of pulse, horizontal. Our new Dual-Pol still has the horizontal pulse, but now it has a vertically oriented pulse as well. So that's the difference. It's the same idea, it's just got horizontal and vertical pulses now. Okay, so that's physically what the difference is between Dual-Pol and our old radar. Now I'm going to talk a little bit about a few of the new important pieces of information that we can get from this Dual-Pol technology. So a lot of you probably are familiar with the base products that we get from our old radar. I'm sure you've heard reflectivity, velocity, storm relative motion, spectrum width. Those are the big things that we get from our old Doppler radar, and we still receive those products. But now we get several new and very powerful parameters from our Dual-Pol as well. So the first one I'm going to talk about here is called the correlation coefficient. We call it CC for short. Basically, what this is able to tell us is information about the size and shape of the objects that we're looking at. Basically, how uniform are the objects that the radar is picking up. So a CC value can range anywhere from 0 to 1. Values closer to 1 tell us that we're looking at objects that are very similar in nature. So if we're looking at pure rain with raindrops all basically the same size and shape, then we're going to have a very high CC value. On the flip side, if you go towards lower values of CC, that's telling us that we have a large range of different shapes that we're picking up in the precipitation. So say we've got a mix of rain and snow, we'll start to see our CC value decrease because we've got a greater diversity of different precipitation types there. So the image on the left is what a CC product will look like on our radar. So basically the things you want to notice, we've got a lot of this area is this kind of purplish red color. And from the color bar up above, you can see that those are very high values of correlation coefficient. So that's telling us that in regions like right here, we're looking at very uniform precipitation. So that's probably going to be all rain right there. Then the other feature of interest, which I'm going to go to in depth a little more shortly, is this ring of yellows and greens here. That's correlation coefficients lower values, telling us that we have a greater diversity of precipitation types in here. So our main applications for this parameter, it helps us locate regions of hail, and it helps us to find the melting layer, which I'm going to go into here now. So probably some of you have heard the term melting layer before. For those of you who haven't, I've tried to depict it on this slide here. Basically, in this region and in most non-tropical locations, our precipitation actually starts out in the upper atmosphere as snow, and then as it falls down through progressively warmer air, it melts before becoming all rain at the surface. So somewhere up there, you've got a layer where the snow is melting. So you've got snow still, but you've also had some that's already melted, so you've got a mix of the two. That's what we call the melting layer. And so that's something that is very important for us to try to figure out where it's at, because it helps us forecast snow levels and what type of precipitation we can expect. So, on the left here, I've got a basic conventional Doppler reflectivity image. And this is basically all we had in the past to try to identify where our melting layer is in radar. And we were relying on a physical phenomenon called bright banding. And basically what that means is when you're looking at a mix of rain and snow, it tends to show up brighter on reflectivity images than if you're looking at just snow or rain alone. So oftentimes you'll have a boundary like this of higher reflectivity values, and that would clue us in that there's snow melting and becoming rain in this area. In this case, it's actually pretty clear, but quite frequently it's a lot more ambiguous than this. You can't really tell if you're looking at a melting layer, or is that just an area of enhanced precipitation. So a lot of times it's pretty difficult to tell just from the reflectivity. Now on the right, this shows how much clearer things can be with our dual-pol parameters. This is our correlation coefficient. And you can see there's a very clear melting layer depicted here. Again, correlation coefficient is telling us how uniform our precipitation is. So this ring here, we've got a lot of yellows and greens. And from our number scale, that's telling us lower values of CC, so more diverse precipitation. So probably a mix of rain and snow in this region. So generally, it's much, much easier to find the melting layer with this new parameter. And here, again, yesterday, we were able to use our new radar, our new coastal radar, to find a very good example of a mixing layer. So here, our coastal radar is located right here. And as that front pushed on shore, we found pretty much a textbook melting layer here. You can see, again, the area of yellow and greens here, indicating very diverse precipitation types, so probably a mix of rain and snow. Based on our radar estimate, we determined that the melting layer top is somewhere on the order of 9,500 feet above the surface. So just for comparison's sake, we looked at our afternoon balloon launch from Salem, which we launched a balloon twice a day, and it basically gives us a real life look at what the atmosphere is like at that time. And we found that our balloon launch indicated a melting layer of 9,600 feet. So our radar was right on the money here. We were able, based on our radar, to very accurately determine this melting layer. Okay. So before I go on to the next parameter, I have a little pop quiz for you here. And I've got to be honest, we kind of forced this in here just because we wanted to work an image of a hamburger into our presentation. We had been working all day at this point. We were getting a little giddy and we were like, oh, wouldn't it be great if we could work a hamburger in? In retrospect, we may have overestimated its comedic value, but I think it's still relevant for understanding our next parameter. So based on the images here, it should be fairly obvious what the answer to this question is. What do a hamburger bun and a raindrop have in common? It's the shape, right? They look kind of similar. And that's very important for understanding our next parameter. When we have large raindrops falling through the atmosphere, air resistance and drag will cause the bottom of that raindrop to flatten, so we'll end up with this kind of hamburger bun-like appearance. So that's very important here with our next parameter, differential reflectivity, or ZDR for short. ZDR basically is comparing the horizontal, remember we have horizontal and vertical pulses now. This parameter is comparing the horizontal reflectivity with the vertical reflectivity. And what that basically means is it's telling us what kind of shape that precipitation has. So if we see a really high positive value of ZDR, that's telling us that there's a large horizontal extent and a small vertical extent to that precipitation. So kind of a hamburger bun shape. And typically that'll tell us that we're looking at rain, and probably heavy rain. On the flip side, if we see ZDR values closer to 0 or even negative sometimes, that tells us that the horizontal and vertical extents of that precipitation are very similar. So we're probably looking at something more like an ice pellet or hail maybe. So we're able to use this parameter for a couple of applications. It's really important for identifying areas of large raindrop size. Again, looking for those positive values of ZDR. It tells us we have large drop size. And also it helps us to identify areas of rain versus snow or hail. Okay, and this is the last parameter. I'm not even going to attempt to go into any scientific depth on this. It's I can hardly understand how this one is derived. But basically, in layman's terms, specific differential phase, or KDP for short, is a measure of the total liquid water content in the radar beam. And for those of you radar junkies out there who actually do care about this kind of stuff, the value is computed using a phase shift in the horizontal beam versus the phase shift in the vertical poles. So when we look at KDP values, we're looking for positive values which indicate the size and concentration of our raindrops are increasing. So I've got a graphic here on the left to try to illustrate this a little bit. Let's start here with the bottom graphic. We've got our radar beams picking up an area of high concentration, large raindrops. So there's a lot of liquid water content in the radar beam here. So that's going to be a very high value of KDP in this beam. Okay, let's contrast to the image on the top here. We've got raindrops at a much lower concentration than in the bottom, but they're the same size. So liquid water content in this beam is much lower. So our KDP value is going to be lower. Still positive because there's liquid water in there, but lower. And then the middle image here has the exact same amount of rain in the same concentration and size as the top image, but now we've added ice pellets in there as well. And the KDP value is going to be the same here because ice has no effect on the KDP. It's purely a measure of the liquid water content in the radar beam. Okay, so with that behind us, now we can try to use those parameters to try to learn more about a case than we might have been able to in the past. So I've got a couple of cases here that I want to show you. Oh boy, I'm kind of running late here. I might just show you one of these cases in the name of time. Let's skip on to the next one here. So the upper left here is showing an area. This is a reflectivity image, something that we've been able to have in the past with our conventional radar. And you can see here, this is an area of very enhanced reflectivities, indicating heavy precipitation of some type. You can see in the colors here, we've got some actually purples and blues. And based on our color table, that is indicating DBZ values in excess of 70. For those of you who are into your radar, you know that's a very high number there. So we can say with pretty high certainty that not only do we have heavy rain here, but we have hail as well. and more than likely some large hail in this storm here. But that's kind of the extent of what we can say about this with our conventional radar. So let's look at what additional information we can get with our dual-pol radar. Okay, so first we'll look at correlation coefficient. So you remember this is the measure of how uniform the precipitation is. So one thing that is quickly noticed here is we've got this area, the left area here that I've highlighted. We've got a lot of yellows and greens. From our number table, that's indicating lower values of CC. So a greater diversity of precipitation types in this area. So that kind of clues us in. We're probably not looking at pure rain here. This is very likely a region of hail. So this may be a hail core. And then on the right-hand side, we've got another area with also very high reflectivities, but the correlation coefficient values are more in this red and purple region. So high correlation coefficient values tell us much more uniform shapes. So we're probably looking at pure rain in this region. Okay, our ZDR, which if you remember, gives us an idea about the shape of the precipitation types. And again, in the area where we thought we saw a potential hail core up here, we've got another very noticeable feature in the ZDR image. We see a lot of yellows, greens, and blues here. And on our number table, that's telling us we've got ZDR approaching 0. So that tells us our precipitation shape is kind of more spherical, not the hamburger bun shape. So this confirms that we're looking at hail in this region. And then on the flip side, where we suspected that we may be looking at pure rain, we've got reds and pinks in here, very high positive values of ZDR. So back to our hamburger analogy, that's indicating wide bun shape. So probably large raindrops in this region. And finally, we'll look at our specific differential phase. So in the area where we previously determined we thought there was pure rain, we see this huge bullseye of KDP here. And if you remember, KDP is the measure of total liquid water content in the radar field. So this is telling us, hey, there's a huge amount of liquid water in the radar right here. So that further goes to verify our suspicion that this is an area of heavy rain. And then on the flip side, the area that we suspect may be a hail core is right here. You can see there's still positive values of KDP here, not nearly as high. So there's liquid water in this region, but not nearly as much. So that would suggest, yeah, there is hail in this region. So in summary, for this case, in the past, basically all we could say is that we've got heavy rain, maybe some hail in here. With dual-pol, we can say, hey, we have hail, and it's probably located right here. So that's a pretty powerful development. Okay, and then I'm going to go through this quickly too, but I wanted to show you guys, because I know there's probably a lot of people who are interested in tornadoes here. Dual-pol is very useful in picking up tornadic debris signatures. Obviously, it's going to be really useful here, right, with all the huge tornadoes we get in the Northwest. You never know, maybe someday we'll pick one up. But this is probably more applicable in the Midwest, but I still thought it was really cool. So right here in our reflectivity image, we're looking at what we suspect to be a debris ball. And that's basically when a tornado is on the ground, it's lofting dirt, pieces of houses, all kinds of stuff up into the air. And the radar picks up on all that stuff. And so you'll often, when a big tornado hits the ground, you'll see this debris ball form. In the upper right, we've got, this is a velocity image. You can see a strong rotation couplet here. So this confirms that we're probably looking at a debris signature. So our correlation coefficient down in the lower left here basically takes any doubt that this is a tornado debris ball. We're looking at very low correlation coefficients. So there's all kinds of different types of objects that the radar is picking up here. So this is what a tornadic debris signature is going to look like with dual-pol. Okay, I think I'm about out of time here. So just kind of to recap, the main benefits of dual-pol for us here in the Pacific Northwest are going to be better snow level detection and forecasting, improved radar rainfall estimates, improved detection of hail cores and storm cells, and this is still brand new to us, so there's bound to be benefits that we have no idea even exist yet. So it's a really exciting time for us as meteorologists here in the Northwest. So I'll take questions now. I want to point you before I open for questions. If you want to learn more about Dual-Pol, there's training opportunities and lots of additional information on the Warning Decision Training Branch website listed here. And you can contact us anytime at National Weather Service. Put your contact info right here. And I guess we'll go ahead and open for questions now.
Yeah, we got to keep flying, so time for about 3 questions, and then what we'll do is once we get to 3 o'clock and we're totally done, anybody that has some additional detailed questions can hang out, ask the presenters here this afternoon, because we want to get everyone's questions answered. So, go ahead.
You see a lot of TV stations now that use a winter type radar where it shows the rain and snow line based on temperature. Do you see that coming out with you guys based on the new radar? Not so much temperature, but the type?
I haven't heard anything about that type of development. We'll probably continue to just put the radar in there as it is without enhancing it. I don't know. I mean, it's possible someday down the road, but I haven't heard anything.
Okay, another one.
Yep.
Oh, they're all on my side. Your boss has a question for you.
Oh, no.
Get to work.
Actually, it's not a question, it's just a clarification.
Okay.
The Dual-Pol radar data will not be available on the website for probably about a year. They're going to wait until they get most of the rest of the country done. The Pacific Northwest was the first place in the country, other than the test sites, to get it. And at that point, we might be able to see some of the things like the melting layer that you talked about.
Actually, I think Mark Nelson had something to add to Tyler's question too.
You were asking if that would show up on TV, was that it?
Well, if they were thinking, no, like on their radars, on the National Weather Service radars.
On the website?
What do you mean?
If it was going to show up on the National Weather Service radars.
Oh, you want to know if it'll show up for the Weather Service?
For the general public? Yeah, for the general public.
Eventually, what? Oh, I'm not the Weather Service.
That melting layer.
At the end of next year, Tyree is right here, the warning coordination meteorologist. As for TV, the vendors aren't sure how to deal with it quite yet, because remember, this has to be for the general public. So you're not going to show a lot of that stuff. So they'll probably make some sort of product like the winter radar, but then you have to have a person interpret it on air quickly. So we'll see.
Next question. I saw some hands over here.
Hey, is this going to be like better for the flood predictions?
Yeah, actually, that's one of the key benefits we're probably going to see. I kind of had to gloss over this because of time, but we're expecting to see improved radar rainfall estimates, basically because we can better identify areas of hail, which in the past, it's been difficult for us to pick out hail contamination from our radar estimates. So now, if we can identify where the hail is, we can take that out before we feed our radar data into our algorithms. So we should be able to, at least in the studies in Norman, Oklahoma, they've been testing this for a while, and they've seen significantly improved radar rainfall estimates. So we should see some of that benefit as well, which will help us with our flood forecast.
Okay, we got time for one more. Maybe on the far side. Anybody? Nobody? If not, we'll just keep going. Okay. Thank you very much, Jeremiah Pyle.